Okay, next we're going to speak about control plane protection, which is the enhanced version of control plane policing. It was added later on in the iOS code. So, but before we go on, both of those options, both control plane policing and control plane protection, are router functions, not layer 2 or switch functions. So, control plane protection, as I said, it's nothing else but an enhanced version of control plane policing, which what this means is that it's going to be a smarter way of doing policing to begin with. Because control plane protection divides that virtual control plane interface into 3 sub-interfaces. So it's going to be 3 queues, 3 different queues for control plane traffic. As you're going to see, we're going to divide the control plane traffic and the management plane traffic destined to the router or initiated by the router into 3 different types of traffics. So we're going to be able to control independently each of those 3 traffic types. So we have different queues for different protocols on how much traffic and what kind of traffic can hit a router CPU. We're going to have 3 such configurations now, not only 1. So it's not going to be an aggregate configuration, a single virtual controller interface controlling everything. It's going to be 3 of them because we divide the control plane management plane traffic into 3 different sub-interfaces. And the reason for that is that, as you're going to see once we define the sub-interfaces, is because we have actually 3 types of traffic destined to the router or initiated by the router. And also when they added this enhancement, they also added additional features to policing. So control plane protection offers also additional features as opposed to control plane policing, which offered only policing. Now we have 3 sub-interfaces. We have the control plane host sub-interface, and as the name states, it's going to give you exactly an idea about what it does. The control plane self-exception sub-interface, likewise, is self-explanatory, and the control plane transit sub-interface, likewise, is going to be self-explanatory. Now, host sub-interface is going to handle IP traffic destined to one of the router's interfaces, or of course, source from one of the router's interfaces, which is like tunnel termination traffic, like a GRV tunnel, for example, or management traffic like SSH, SNMP, syslog, so any kind of management traffic destined to the router. And partially is going to cover some routing protocol traffic. EIGRP and IBGP are well known to fall under this host sub-interface. Now so by the name is going to be control plane or management plane traffic destined to the host, to the router itself. Self-exception sub-interface, as the name states, is going to handle traffic redirected to the CPU as a result of a self-exception. Also, this interface handles control plane IP traffic queued by the interface driver and also non-IP traffic. So non-IP traffic like ARP and layer 2 keep alives are going to fall down under the self-exception sub-interface. And LDP, OSPF, and eBGP are other kind of protocols which fall down under the self-exception sub-interface. Now, even though both LDP, OSPF, and eBGP are still destined to the host, to the router itself, they fall down under the self-exception sub-interface based on the way of those based on how those protocols were implemented on the iOS devices. They are actually, that traffic is queued to the CPU by the interface driver, not by the specific process. So because these protocols are definitely controlled behind the scenes inside the router, that's why they fall under a different sub-interface, because ideally you would want to see also SPF, NB, EBGP, and LDP to be on the host subinterface, because there's still traffic destined to the host, which means to the router. But because behind the scenes they are differently, let's say, manipulated by the router, they fall under this subinterface of self exception. Now the transit subinterface, as the name states, handles transit IP traffic that is process switched by the CPU. So transit IP traffic, not traffic destined to the router. So one example is going to be tunnels non-terminating on the router are an example of such traffic that are handled by the transit subinterface. So like if for whatever reason the router has a tunnel transiting the router, which has to be process switched, then it's going to fall down under the transit subinterface. As the name states, again, it's going to take transit subinterface is in charge, handles transit traffic not destined to the router, which is going to be in the end process switched by the router. Now, as I stated, control plane protection adds additional features. So adds additional features to better protect the CPU of the router. It supports port filtering and queue thresholding. Now, port filtering, what that is, it's an early drop of packets directed to closed or non-listened ports of the router, which means before hitting the CPU. So what this means is that, as I stated before in the other example previously, let's pick up this router. Again, a router, and we divide this again into 3 regions. We're again upper in the first region. We have the, let's say, the router's interfaces. And here we have the CPU of the router at the bottom, and in between we have our control plane, CPPR, control plane protection, with the port filtering capability configured. Now, assuming that my router has enabled only SSH, and HTTPS traffic, control plane wise. So we can manage the router via SSH and HTTPS, but not via Telnet and HTTP, for example. It means that if we configure port filtering with CPPR, because the router doesn't have TCP port 80 opened and TCP port 23 open, because it has those services disabled. Those services are not running on the router. And if we configure port filtering, what's going to happen is that if the router receives an incoming session of type Telnet or HTTP, which is clearly targeted towards a service which doesn't run on the router, a closed port, it's going to be instantly dropped by the port filtering functionality. Without this functionality, that traffic is going to hit the CPU, and the router is going to say, I don't run the service, I'm going to drop the packet, but it still hits the CPU. And queue thresholding is meant to limit the number of unprocessed packets for a specific protocol, which means how many packets which have been unprocessed destined to the router's CPU can I allow to be queued, to stay in the queue. So it's a further enhancement to also limit, not only to do input policing to control which traffic is allowed to be destined to the router CPU, and so what kind of traffic, PR, BGP, and how many packets per second, but also how many packets can I keep in the queue. Because once I configure the limit, let's say I'm gonna allow the router, let's say with this feature, with control plane protection, I'm gonna do, let's say, an input policing, which I restrict the router to, let's say, receive not more than 100 EIGRP packets, correct? But the challenge is that, so my input policing feature states that I allow no more than 100 packets per second of type EIGRP. So my configuration is going to make sure that not more than 100 packets per second of type EIGRP are going to hit the CPU. But what happens is that those packets are going to be sent to the CPU if the CPU is available. Actually, what happens, the CPU goes and grabs those packets when it has time, allocated time to process those packets. So till the CPU has, hey, I'm free to process those packets of maximum 100 packets per second are queued by my control plane protection or policing functionality. So this capability in here further restricts, okay, if we queue those packets, they are in the configure limit, but those are queued because the router doesn't have time now to deal with those packets. How many packets can we keep in the queue actually? Configuration wise, makes use of MQC syntax just like control plane policing, but of course we're going to apply the policy map on the different virtual control plane interfaces. We're going to have the control plane host subinterface, the control plane self-exception subinterface, and the control plane trans subinterface. So it's just going to be a difference of where do you apply the configuration, but otherwise matching the traffic, class map ACL, and policing or the function is going to be the same thing, just control plane policing. Control plane policing, yes. Verification wise, the same two commands to verify the class maps and the policy maps. Now when we verify policy and statistics, now we say show control plane, and we don't say aggregate, but we say for which of the virtual control plane subinterfaces do we want to verify the features if it was enabled, or the counters, which means how many packets have been allowed or dropped. So you say show control plane host counters, which means show me how many packets have been dropped or allowed on the host subinterface. And likewise, if you want to verify the detailed statistics, you say show policy map control plane, so still the control plane interface, but then you say for which subinterface, for the host subinterface, for the transit, or for the self-exception one. Okay, before we go to the configuration part, there's a question from Matthew. So the default class map is always at the bottom, correct, Matthew? It's like in any other kind of MQC syntax implementation, whatever traffic is not matched by user configured class maps is going to match on class default. And as I stated, traffic is the policy map is always inspected top down, and the router is going to stop on the first class map match and take action as per that class map. So you can, one traffic type cannot match in multiple class maps. Matthew says this is protection, not policing. Slide says policing. Let me check that out. Correct, thanks for that, Matthew. So that was a typo from my side. It says protection. So control plane protection verification is going to be as I stated in here. Now configuration wise, we're going to do the same thing. We're going to go on router tree, and we're going to apply on router tree input policing for EIGRP traffic, which should be under the host subinterface, and input policing for ARP traffic, which should be under the self-exception subinterface. So let's go on router tree. So pretty much we keep the same EIGRP configuration. We just apply it in a different place now. We apply it under the control plane host for EIGRP. So we say no this. And now we say control plane host, and we apply that feature. So now verification wise is going to be show control plane host features, Control plane policing has been activated because this is still policing but on the host sub interface. And counters, likewise, how many packets have been processed and dropped? 500. Verification wise, show policy map, control plane, host. And we see pretty much the same thing. I have on the host sub interface this policy map applied, which contains this class map, which states that if more than 100 packets per second of type BR are being seen, drop them. But of course, I don't hit that limit. It's confirmed 9 packets. And on the class default, I see nothing in there so far. Now let's try and also do look on the ARP side. So I'm going to say class map, CPP, ARP, Mesh Protocol ARP. Let's see if this is supported. Mesh Protocol ARP, exit, policy map. This is going to be named now Ceph. It's going to be calling PMAP, some policy map for Ceph exception. And we say class CPP ARP. And we say police rate. Let's say 10 packets per second. Confirm action. Transmit exceed action. Drop. And now we go under control plane, Ceph exception, and we say service policy input, service policy input, PMAP Ceph exception. So ARP is allowed in the match protocol function, but EIGRP was not. As I said, it depends a lot on the platform and on the code you're running. So show run class map. We have now this class map matches on protocol ARP. Show run policy map. We have now the policy map of Ceph exception, and I'm saying for ARP traffic, allow 10 packets per second. Otherwise, if it's more than that, drop it. So show control plane, Ceph exception features has been activated. So this confirms that the feature is active, has been enabled. And counters, 33 packets have been processed, 0 have been dropped. Show control plane, show policy map. Now verification wise, show policy map, control plane, Ceph exception. So we see that for protocol, we see that we have this PMAP policy map applied inbound. And for the class map of type ARP, no packets have been matched. So confirm 0 packets, probably because ARP has been pre-built. It makes sense because we know that for Ceph to work, when the router boots up, and when it learns about routes to any kind of IGPs or BGP or static routing, it's going to always preemptively ARP for the next hops to pre-compute a Ceph table. So far it makes sense that we see no traffic matching on our configuration. So we're gonna clear the ARP table to see if we have traffic matching in there, and we have a lot of other traffic matching on the class default likewise. Let's say show IP ARP. Actually, let's say this show IP interface brief. Let's do this, and let's shut down one interface to clear the ARP table. Let's say FA00. Shut down. So do show IP ARP. The ARP table should be gone. And no shutdown. First of all, the EIGRP should come up. Show IP ARP. This is for myself. Now probably EIGRP doesn't come up because port fast is not enabled on the switch, so it should take those 30 seconds to go to forwarding. We should wait 30 seconds more. So on the switch side, if we say show spanning tree interface FA103, there we go. Now it went to forwarding probably. So now router 3 should bring up the EIGRP neighbors. There we go. And ARP should have been likewise pre-populated. And now if you look again at our show command, verification command, There you go. We see 3 packets have been confirmed. So it was as expected an order of operation. So we saw no ARP traffic being matching on our configuration because the router has all the, let's say, next hops resolved, pre-resolved before we applied our configuration. So we had to clear the ARP table to make the router ARP again for the next hops and to see the traffic in there. Question from Matthew. So shutting just one interface clears ARP cache question. So it makes sense, right? So whatever ARP interface the router has on an interface of himself, if the link goes down, the ARP entries which he had learned on that interface are going to be cleared, because it doesn't make sense for the router to keep useless information to consume memory on the router for something which is not required, correct? Because, for example, if we say, I use the shut no shut because for a specific reason. If you say show IP ARP, and we say debug ARP, and we say clear IP ARP for, let's say, router 1, what I want you to understand is that the clear IP ARP function forces the router to clear the ARP entry and to send a new request. So clear IP ARP on IP address, clear the IP to MAC binding for that IP, doesn't mean remove the entry. It means remove the entry and send a new ARP request, because you do this command when the MAC address of that IP has changed to refresh the MAC entry. So this is not like a deletion of the ARP entry, but it's going to be a refresh. As you can see, it got refreshed back again. Okay, another question from Matthew. Did it clear all the ARP? So only the ARP entries which were pointing on an interface which I shut it down, and it makes sense, right? So if a router has 10 links and it has, let's say, 5 ARP entries out on gig 00, if you shut gig 00, it's going to clear only the entries out on gig 00, not the other entries, correct? It has to make sense, it has to be logical.